Right, go ahead.
So we are very pleased today to have two speakers from Paris, because they are both at the moment in Paris, who are Hervé Moulin and Matías Núñez. The first speaker will be Hervé. We will talk about universal guarantees in bargaining. And after the usual coffee break, virtual coffee break, we'll have Matías Núñez, who will talk about voter coordination in large elections, a case for approval voting. For those where I guess everybody is more or less familiar with the seminar, so if you have a question, you can just put this on the chat, and usually we will review the question after the talks, and unless it's a very precise clarification questions. And now I think the floor is for you, Hervé.
Thank you very much. Let me.
Of course, you can mute your microphone and cameras.
All right. So this is a paper in construction with Anna and Fedor Sandomierski, and it's part of what I like to call the program of worst case implementation, which is in some sense the one started by the cake cutting literature many years ago, more than 70 years ago, when procedures were invented in which the only real property of the procedure was to guarantee a fair share of the cake. You have heard about things like that in Anna's talks. So I'm not going to go too much on the generality, but the idea again is, can we guarantee some level of welfare to participants? And the question is, what do we understand by guarantee? So I give some basic example. A guarantee can have an exogenous character, like in when you exchange goods, the voluntary trade constraint. I mean, that's the guarantee that you will not be forced to trade in a way that's disadvantageous. Similarly, disagreement outcome in bargaining that could represent an outside option. And now I'm interested here in an endogenous version of guarantees, which is the one the one I will be looking at is in the context of bargaining. And bargaining here, I will think of it as being voting with lotteries. I mean, I put voting, it's the classical bargaining model, in fact, with deterministic outcome, and then we can choose a compromise by means of lotteries. So to get the idea, so that everybody has an idea of where I'm going, I'm going to show you first a picture to illustrate three typical examples of guarantees, which will play a role later on throughout the talk. And this will be the average guarantee, the random dictator guarantee, and the median veto guarantee. So here is the picture. So you see on this picture, you have the shaded area, which represent a typical bargaining problem in which there is no singled out disagreement or special outcome. So this is the set of utility profiles that are feasible for my two agents, 1 and 2. Okay, and of course you have the Pareto frontier and other points which are not efficient. So when I speak about the average guarantee, what I mean is for agent 1, a certain function gamma of U1, so be careful, that's the key thing here. The gamma only depends upon the U1, namely the utility values of agent 1, namely these 8 first coordinates of my 8 points. So again, when I compute for agent 1 the average utility of these 8 values, I get his or her average guarantee. Now you are now clearly, if I do the same for agent 2 and I compute the average of the 8 values of the second coordinate, I get another guarantee for agent 2. And if I put them together, gamma of U1 and gamma of U2, where am I? Well, of course, I am at the barycenter, right? And the barycenter of the shaded area is, of course, feasible, namely below the Pareto frontier. So this isn't a feasible guarantee, okay? Now, random dictator, that's a different kind of guarantee, but notice I'm not gonna say that the corresponds to the midpoint of A and corresponds to the outcome we expect to arise in this particular problem with these two agents if they actually play random dictator. What I'm interested in instead is agent one is considering ex ante a mechanism in which he is told that whatever he does, whatever the other agent is, it's possible for agent one to guarantee a level of utility which is 1/2 of the utility of C plus 1/2 of the utility of A, because agent one knows that he has essentially, as a safety level, 1/2 of a chance of being the dictator and therefore securing the utility of A, and 1/2 of a chance that somebody else is dictator, and without any information about who that somebody else is and what preference and so forth, agent one knows that he's not going to go below C. So the guarantee here is a function that only depends upon your own utility, that in this case, the 8 numbers. And the last one was the median veto guarantee. That's a different one in which we say, okay, well, we will give agent one the possibility to eliminate at least 3 outcomes. Well, since 8 is an even number, what we can do is give agent one the possibility of eliminating 3 outcomes, then give agent two the possibility of eliminating at the same time 4 outcomes that will leave for sure at least 1 feasible outcome. And then alternatively, we can give 4 tokens to agent one, 3 to agent one, 3 to agent two, and make an average. So you see that this way, I'm going to create something which has the advantage of being decentralized and feasible. So that's the concept, and that's the thing we want to study. I mean, given that there are easily constructible examples like that, in which space are we moving? What are really the options? So the model has a finite set of outcomes, and on which we take, those are the, if you wish, the deterministic outcome. We take convex combination of them. We have a finite set of agents. And this matrix here of utility indexed by agent and pure outcome represents the preference profile, the utility profile. And then we generate a set of feasible utilities, just like we had on the picture by taking convex combinations of the outcomes. Okay. What we call an individual guarantee. We will not be talking at all about coalitional guarantees in this talk. The key property that it has to be feasible no matter what are the choices of these utilities U1, UN. And you realize, of course, that because gamma depends only on one of the functions, there is a serious issue here of feasibility. And feasibility, I simply mean that this vector belongs to the comprehensive hull of the feasible set. So it could be even way below the feasible set. Properties that we use, that we add to limit a little bit the options. Well, essentially, we think of U as von Neumann-Morgenstern utilities. And therefore, just like von Neumann-Morgenstern utility, we should respect covariance. Multiplying the utility by a positive number or adding to the utility a constant at every outcome, those operations are essentially meaningless. I mean, they don't change at all the results. Monotonicity now simply says that whenever your utility increases, quite naturally, your guarantee should increase. And finally, we have 2 basic symmetry property hardwired in the model. One is anonymity. That one is hardwired in the model, not the other one. Simply the fact that this function gamma does not depend on the agent I. I mean, it's the same function gamma for each agent. So therefore, this is anonymous. And neutrality, the usual neutrality in outcomes, here, as a very important consequence, is that since your utility U is just a list of P numbers, and now it should not matter to which particular outcomes those numbers attach, then you immediately realize that gamma is actually only a function of the vector U star, which is the rearranged vector where we take all the coordinates of U and we rearrange them increasingly. So this notation here, U star 1, U star 2, etc., is very important. So for instance, just to be sure, U up star 1, that's the minimum of the utility of agent U over all outcomes A, the pure outcomes A. And of course, U star P is the maximal utility that's feasible for agent, for this particular utility. Okay, so that's the concept. And we just gave some examples. The average guarantee was simply the 1 over P of the sum of all the utilities, right? Which could also be the sum of all the U star K for obvious reasons. The random dictator, what was the random dictator? Where 1/n of the time I'm allowed to be the dictator, so then I guarantee my best utility, and the rest of the time somebody is dictator. Before entering the mechanism, I have no idea who could be that somebody, so therefore I expect the worst with probability n-1 over n. Finally, the median veto. Here there is a typo. It should be that if P is odd, then you get, each of us gets a number of veto token, which is P minus 1 over 2. Now, actually, there is no typo. The number of token is P minus 1 over 2. So for instance, if P is 11, then P minus 1 over 2 is 5. So each one of us has 5 tokens. And the next result, the net result is that at the minimum, I get the utility U star 6 because I can eliminate 5 of them. So, okay, so that's when P is odd. And when P is even, we cannot have such a clean cut, but we do, as I explained, an alternative between either giving you P over 2 minus 1 veto token or P over 2, and you take the average and you get something which is feasible. So you see those 3 actors, and again, the question is, why those 3? You know, what else? I mean, maybe some very strange, different animals live out there. So there is one last design goal that's important, is the notion of maximal guarantee. I mean, of course, in the end, you know, this is a welfare concern. We are trying to get as high guarantees as we can, because this is what will help at the best we can the participation, you know, make people feel good about participating in the mechanism, because it cannot go too bad for them. So that's the standard notion of maximality. We'll say that gamma tilde is maximal if there would exist another guarantee which is always above that one, then in fact they have to be equal. So it's not possible to find another guarantee that would weakly improve all the time and sometimes strictly improve. Those are the interesting ones, the guarantees, the G tilde, and that's the set that we would like to understand. An example, the average guarantee. That it is maximal, and I will show you why in part in a moment, but it's not an obvious statement, right? I mean, it doesn't look like it's difficult. In fact, it is not difficult. Still, there is some work behind. But now, what else? And that's a big, complicated question. So what does the paper do on this question, which is really the question we would like to solve more thoroughly? We are not yet at the end, to characterize this set G tilde. So we'll show a case where the answer is trivial, an important case, as you will see. But then we will show that in any other case, the answer is very complicated. And I really mean it. And then last, we will use a simplifying assumption, which is an assumption of partial additivity, familiar in the literature on inequality measured, like the Gini index and so forth, which are rank additive, namely additive with respect to the increasing order statistic. So then in that case, we can get a full answer with 2 agents and some hopes toward an answer for more than 2 agents. All right, the easy case. I said there is a case in which everything is trivial. Very simple. If the number of agents is at least the number of outcomes, then the average guarantee is the only maximal guarantee. In other words, any guarantee that is feasible in that case must be dominated, must be below the average guarantee. So the problem is solved. Forget about random priority, forget about veto. They will not give you any, you could introduce those features in your mechanism, but they will not change the basic worst case level. And if you are concerned with having a worst case level, then you should make sure that this is achievable for everybody. Okay, so why is that? It's very simple application of using profiles, which are cyclical a la Condorcet. Take the case for simplicity, n equal 5 people, 3 outcomes. Take any utility U, which is defines for 3 outcomes A, B, and C, the utility UA, UB, UC. And now I construct a profile where there is U, then there is the permuted once of U, UB, UC, UA, then permuted twice of U, UC, UA, UB. So it's a classical cyclical pattern. And then since I have more people than outcome, I fill it with zeros, agents who don't care about anything. Now by feasibility, the sum of the gamma applied to U sigma square, and 0 should be feasible, less than UA plus UB plus UC. But by neutrality, I know that gamma of U sigma, and U sigma square, they are all the same. And by covariance, clearly gamma of 0 must be 0. Therefore, gamma of U, since the total is here, gamma of U is at most 1/3 of UA plus UB plus UC, and that's the average. It's obvious that you can do that for any n and p as long as n is greater than or equal to p. So it's interesting because what it tells us, since we're going to be discussing voting by veto and things, and random dictator is also a voting by veto rule, right? Because it's half of a chance of being full veto for me and half of a chance of having no veto. And so in fact, they are exactly the same family. And what this very simple result says, but I don't think it's been discussed systematically like that, is that this is useless if you have more people than outcomes. In fact, in reality, we know that voting by veto is not really often used, except when you have a small committee and a large number of outcomes. Okay, now if n is strictly less than p, it turns out that G tilde is of infinite dimension. And this is true even in the case of 2 and 3. So now let me ask Vincent how many minutes he allows me generously. Vincent?
5 minutes.
5. Okay, he's tough as usual, but I was expecting that. Okay, so I'm going to skip. I'm going to just give you a picture. Okay, in the case of two agents, and this is the case of 2 agents and 3 outcomes. So in that case, by covariance, when you have a utility function, a von Neumann-Morgenstern one, you can conventionally bring it to the level, bring it to U equals 0 for the lowest utility, 1 for the max, and then your only parameter of individual utility is the x in the middle between 0 and 1. So therefore, your guarantee becomes a function small gamma of x of corresponding to the utility 0x1. So now the theorem here for such guarantee to be maximum. never mind the expression. Let me just show you the picture. It's going to be like this. If x on the horizontal line is, remember, the value for you of the middle alternative, the one that you value just in between the two extremes. So it goes from 0 to 1. And then this is your utility for that middle. This is going to be the guarantee gamma of x when your own utility for the middle is x. So what you find here is the random dictator would be that horizontal line, because the random dictator gives you half of a chance of your top, half of a chance of your bottom, and completely ignores the middle. So the gamma is the horizontal line. The veto gives you systematically as a guarantee the level of your middle utility, because you are given one veto token. So then the gamma of x is the diagonal, right? And the average is in fact simply a 2/3, 1/3 average of those two. So it's a line that starts here at 1/3 of 1, somewhere here, and then goes straight through the midpoint to the other side, because these curves must all be symmetric. But then on the picture, I represent an infinity of possible curves, because I can vary the point alpha between 0 and 1/2. And from each alpha, you construct this figure here with these two quadrilatères, these two polytope with 4 vertices. And then you have one function which goes like this, and another one which goes horizontal, a bit like random dictator, and then becomes veto, and then back to horizontal. So it's not very complicated once you take the time to look at it. It's various, you can obtain it by various mixtures of veto and random dictator, but it is of infinite dimension, because in between I can plug any curve provided that the derivative satisfies some bounds. So it's a very rich set. And to a certain extent, it's not of really practical interest to understand fully the structure for any n and p. And in any case, we would not be able at this point to say anything very useful. So what we do to try to get more leverage and progress is to make the rank additivity assumption, namely that your guarantee is actually going to be a linear combination of your various level of utility. I mean, notice that this is exactly what was happening so far in the methods that we looked at, because the random dictator was a combination of your U1 and UP. The median was also a combination, etc. So it's not going away from the important family of guarantees. But even that is going to be difficult to characterize, except in the case where you have two agents. If you have two agents and 3 or more outcomes, then it turns out that a guarantee, an additive guarantee of that sort, which is a linear combination sigma lambda k u star k, is feasible and maximal if and only if the distribution lambda is symmetric, namely lambda k is equal to lambda p plus 1 minus k. What this means is that the extreme point of that polytope, I mean, of that simple subsets of the simplex of lambdas, are very easy to describe. They are what we call the fair veto guarantees, because they are exactly what you obtain when you move in discrete steps from the random dictator, which is half of your worst and half of your best, to the median, which is, let's say, exactly your median all the time. So now you do maybe half of your second worst plus half of your second best. That another one is half of your third worst and half of your third best, etc. So it's simple, and it's also, I think, useful because it gives us a sense of, where the mechanism designer can try to choose depending on the type of problems, you know, what kind of guarantees would make sense. I mean, in one slide that I went to very fast, we make some comments on that. I mean, if you think, just sticking to the case of 3 outcomes to stay simple and comparing the veto to the random dictator, it seems plausible to say that veto is going to be the natural choice when we have a very risk-averse and vision of the, you know, the possibility that the exposed would be very long-term. You know, we elect someone to a lifetime position like a pope or a Supreme Court judge, or we choose a facility for a large infrastructure. And whereas the random dictator is more appealing when the randomness or the compromise comes from time sharing or budgeting, if it's in the context of participatory budgeting, such as, you know, we choose a restaurant. So today you choose your favorite restaurant, but tomorrow I get one, and so forth. So of course there is, on the empirical side, there is potentially work to do there, which we do not address in the paper. All we do is to notice at this point that if you extend this notion of fair veto guarantee to any number of players, that's very easy to do. For instance, if you have 3 people and 11 alternatives, you could say, okay, I give 1 veto token. As long as you distribute 10 veto tokens, you will be fine. So I will give to 1 person 1 token, to 1 person 5 tokens, and to the last person 4. But then to respect fairness, I will randomize uniformly over these 3 positions and compute the corresponding utility level. So that gives you a guarantee which is of the additive type and is certainly feasible. One would hope at first glance that, just like in the case of n = 2, this is still a maximal guarantee. But unfortunately, that's not the case. Unfortunately, even in the simplest case where you have 3 agents and 4 alternatives, so the simplest case after 2 agents, it turns out that, you know, doing the veto guarantees corresponding to either you give 1 veto token to each, or all the tokens to 1 person, or 0, 1, and 2 to do the compromise, you end up with 3 guarantees which are good, but the one which is not good is this one, the random dictator, 2/3 U1 plus 2/3 plus 1/3 U4. And when I say not good, it's because it's not maximal, and in fact, it is dominated by 1/3 U1 plus 1/3 U2 plus 1/3 U4. So it's possible, and that's because of the combinatorics of 3 agents and 4 alternatives. It's possible to give better than the random dictator, and also easy, of course, to design mechanism, a simple mechanism which achieves that. So it still remains a big open question for us to have a better grasp on the set of maximal guarantees in this problem for 3 agents or more, and fewer alternatives, fewer agents, than alternatives. I guess it's about time I stop. Thank you.
You can unmute your microphone and make a round of applause. And we had 3 questions in the chat. The first is by Nisa.
Yeah, so I had a question about the simple lemma that you showed earlier, where the number of agents is at least the number of outcomes. So did the lemma say that the average guarantee dominates every other feasible guarantee, or just that it's undominated in some example? So
no, dominates.
Okay, so in every example, the average guarantee is at least as large as the, okay. So that one example wasn't the complete proof, right? That one example with the
yes, it was because we were starting from an arbitrary U.
Okay.
Started from an arbitrary U, and then you use critically the neutrality. So you show that for this arbitrary U, the gamma of U must be less than the average utility.
Right, but I was just thinking about what happens in other scenarios where the profile is not cyclic. even in those examples, would it be true
yes.
that the average guarantee is at least as large as any other feasible guarantee?
But those, you cannot construct a guarantee based on the profile. The point of guarantee is, since it's only built on the individual thing, once you say that any guarantee must be below that, that's it. That's the end of the story. Okay. Of course, guarantees are typically much below, the profile of guarantees is typically much below. But yes, no, this simple lemma is indeed really simple.
Okay.
But the surprise is, as soon as you don't have that, you say, oh, I'm going to tweak it and get something. And no, it becomes extremely hard. I mean, because we have indications. In fact, we start to suspect that if you do a continuous version of the model, it becomes as complicated as the Monge-Kantorovich transport problem once you put it in a continuous version. And that, of course, is the matter for high-level mathematics.
I see. Thank you, Hervé, for the great talk.
Thanks.
We have a next question by Matías.
Yeah, well, actually, my question, I asked the question before the slide you showed us the different guarantees with two voters. But so my question maybe can be rephrased to say, but if you consider only ex post guarantees, right? The median veto seems to be the most relevant one, or maybe I'm misunderstanding things, but you know.
Well, it has to do with the interpretation of the von Neumann-Morgenstern utility.
Mm-hmm.
You know, if you are a von Neumann-Morgenstern type, you look at the mechanism ex ante as an expectation, and you are happy right there. I mean, you are risk neutral in that sense. If you are in fact more concerned by the ex post thing, and you are risk averse in that sense, then you go toward the ordinal model. And of course, there is a legitimate ordinal model here where your utility is simply the worst deterministic outcome, the utility of the worst deterministic outcome. And then the veto token are obviously the only rules you can use. I should probably have, there is this initial remark, you have two people, no lottery, no nothing. What can you do? The only thing you can do is to give them.
I mean, I understand the
it is
the paper is to enlarge it, but just to make a connection with the.
It is definitely the median veto is the dominant one when you have only ordinal data and ordinal tools. Yes.
Okay.
Yeah.
Bill has had a question too.
Yes, I think, Hervé, there must be something I'm not quite understanding about the model. Suppose we had one of these feasible regions and we added a large number of additional corner points, all very close to one another, but barely pushing out the convex hull. Then we're going to have almost no effect on the actual feasible region, but an enormous effect on, say, what the average of the corner points are. Is that a problem?
No, it's absolutely true. I mean, the guarantee may or may not be very close to the frontier. You are not making any real statement vis-a-vis the actual Pareto frontier for an actual complete profile. You are just saying, you're just taking this view of the ex ante person who is wondering, should I participate when I have no idea where, what kind of other participants will be there, you see? So, yes, sometimes the guarantee can be very close to optimal, sometimes not, but there is nothing we can do about that.
I was more thinking that in some sense, these guarantees are discontinuous as a function of the region, because small changes in the region have big changes in the guarantees.
Oh, well, yes, that's correct. That's correct. But they are not defined only from the region. They are the region and the points. But yes, you're right. You're right. There is some potential discontinuity there. Yeah, yes. Thank you.
Good. So if we don't have any other question, we should thank again Hervé.
Thank you.
And we will let Dominic put us for those who wish to. in our virtual coffee rooms. So our second speaker today is Matías Núñez, and we'll speak about voter coordination in a large election, a case for approval voting. And it's a joint paper with François, who I've seen, and Antonin. I'm not sure if Antonin is here, but I guess François could answer questions too if there are some questions. So Matías, the floor is yours.
Thank you. Thank you, Hervé. Thank you for having me here. Thank you, Hervé, for the presentation. Thank you, Vincent, for the presentation. Let me put the full screen. Okay. So as no, I mean, it's not working. 1 second. Okay, so now it seems to be working. So as Vincent said, is a joint work with François in Nokia Research and Antonin, who Antonin couldn't make it. He's teaching these days, this afternoon. So it's about approval voting. Okay, so I mean, it's has nothing on vetoes on the paper. So let me say a couple of words about approval voting. I will try to show you what we want to do in this paper. So it's a joint work between computer scientists and economists. So I think is a very good seminar to present this paper. So I mean, yeah. So as I mean, this is very classic, but I think if you don't really know what approval voting is, it's a good idea to refresh the ideas, right? So as early as Borda, right, we know that the plurality of voices indicates the will of the electors only when we have two candidates, right, and not true with more, right? So namely, in multi-candidate elections, when a candidate wins, doesn't really mean that he's the will of the majority, right? So typically, when voters are split or candidates too close, a minority candidate can win with less than 50% of the total votes, right? So we can have typically a difficult coordination for voters, and we can also have legitimacy concerns, right? If the winner doesn't get more than 50% of the votes, then well, maybe that means something, right? About how much the voters like this candidate, right? So in order to avoid this vote splitting or legitimacy concerns or well maybe all these problems, in the 70s or so, in two centuries later, Steve Brams and Robert Weber, among others, okay, have started advocating approval voting, okay, which is a simple twist in the electoral. So approval voting, I will talk about approval through the whole presentation, is this area in which you can vote for as many candidates as you want, right? So typically the logic would say that since you can vote or you can approve as many parties as you want or as many candidates as you want, for instance, those with a similar ideology, all of them, and you don't have any fear of splitting your vote, then it should avoid these problems of vote splitting, right? So it should help voters to coordinate. But now, that's the logic, right? That's the logic, or that's what we ideally would have in mind when we propose this system, right? And now, in order to formalize this principle, right? Okay, approval voting helps voter to coordinate. I mean, we can use several methods, but what we are going to do in this paper is to focus on these models of electoral equilibrium, right? So in a model of electoral equilibrium, what I do is I say, okay, voters are strategic, right? And then what I'm going to do is I'm going to compare voting rules by the equilibria they lead to. So there is a huge literature on electoral equilibria. Here I'm citing all 4 papers, which are the mostly related to us, right? So Meyerson-Weaver being the starting one, then Meyerson 2002 on Poisson games. Lallier has a similar spirit. I go back to this in a second. And Bouton-Castañeda, who makes a comparison in the divided majority setting. So overall, what gets out of this literature is that approval voting is better performing than plurality voting. Okay, that's almost a consensus thing. The key idea is that there is an uncertainty on the number of voters, on the scores of the candidates. This makes everyone pivotal, right? And well, we can show under certain conditions that approval voting gets to better equilibrium than other rules. However, these results are incomplete in the sense that voting rules lead to a vast multiplicity of equilibria in many situations. So unless we make strong assumptions, comparison between voting rules is pretty difficult, right? Because once you have several equilibria, it's not so clear what we mean then by approval voting is better performed. So what do we do in this? Paper? So here, this paper, we are first going to build an algorithm, okay? And the algorithm is going to be very useful for what we do in the whole paper. And this algorithm, which is based on this game theory model, is going to allow us to compute equilibria at any preference profile. We're going to show that the likelihood of bad equilibria is very low. And then in the final part, we're going to study a model of learning, okay, based on these Poisson games, where actually voters revise their behavior in a progressive manner. And we're going to show that with a very large probability, approval voting almost always selects the convex winner. So that is, I mean, we get a very positive conclusion on approval voting here in this model. Please, if you have a question, no, I mean, I have to answer the question at the end. So now, let me go into some more precise presentation. So here on the presentation, I'm only going to talk about plurality and approval voting. There are other rules we tackle in the paper, such as negative voting. I won't be talking about this in the presentation. So we have two rules. First is plurality, right? That I guess everyone knows. Each voter votes for one candidate, and the candidate with the most votes wins. This is used in many elections, right? And this rule has, in these electoral equilibrium models, has one problem. It's called the Duverger's law problem of Duvergerian equilibria. Namely, we take any two candidates, and you assume that everyone votes for his favorite between A and B, and this becomes a self-fulfilling prophecy, namely, either A or B wins the election. The problem of this is that the winner of the election is a priori disconnected from the true preference of the electorate. I will show an example in a minute to show you this Duvergerian equilibrium. So here, the alternative we propose to plurality, or has been proposed, is approval voting, right? So I'm going to talk only about 3 candidates elections. So each voter is going to vote either for 1 or 2 candidates, right? So this rule is popular among voting theorists. There is a paper by Jean-François Lallier on this, in which voting theorists vote on their favorite rule, and actually approval voting is the most popular one. It has been approved in 2020 in 2 local elections in the US, in Fargo, in North Dakota, unless I'm mistaken, and in St. Louis in Missouri. And so with 3 candidates, A, B, C, it gives us 6 possible ballots. So either you vote for A, for B, or for C, as usual, or you double vote, right? AB, AC, or BC. And the logic of approval voting is that it escapes from Duverger's law, right? Why? Typically, independently of your beliefs, it is always rational to approve of your top candidate, right? Since you don't care about the relative likelihood of this candidate to win, right? So typically, the equilibrium are not going to be Duvergerian because everyone can vote for his top candidate. So we should not have only 2 candidates getting all the votes in this equilibrium. So now to show you, so what I'm going to do, I mean, I cannot show you the algorithm. So what I'm going to do is I'm going to show you an example, right, in which I show you why approval is better than plurality in a simple setting, why approval is not perfect, and then I will show you the data that the algorithm gives us that suggests that actually these problems of approval are not that serious as expected, okay? So what we have is a setting, okay, it's a very simple setting, so it's a single peak profile, where I have 60% of green voters and 40% of blue voters. The green voters have, so this line means it's the utility function of green voters, and this is the utility function of blue voters, right? So that the green voters prefer A to B to C, and the blue voters prefer C to B to A. So here A, right, it has a red arrow, a red line here because it's the convex winner, only A should win, right? When B is low, A is the only reasonable idea, and here we're really in the spirit of Condorcet. So here, what happens in this situation? Suppose that we consider equilibria in this game. Let's say they vote with plurality voting. So the green voters, suppose that everyone thinks that either B or C is going to win the election. So the green voters start voting for B, the blue voters start voting for C, right, as here. So this generates the following scores. A gets no votes, B gets 60% of the votes because he gets all the green votes, C gets 40%, and this generates that BC is the most likely pivot, right? So this is typically, so since pivot BC is the most likely pivot, then actually B and C are the only rational best responses, right? So this is the Duverginian equilibrium, and this is the bad property of plurality voting. So a naive analysis of approval would say, okay, what happens in this example with approval voting? Well, simply, what we say is we don't change preferences, we just change the rule. So we allow the voters to vote with approval voting, right? And then what happens? Well, simply, in the same profile, right, 60% of green voters and 40% of blue voters, now all the green voters, even though they think either B or C is going to win the election, they vote for B and for A. Why? Because A is their top candidate, right? Since A is their top candidate, now the scores in the situation in which everyone thinks that B or C is going to win the election are these ones, 60, 60, and 40, so that A becomes the most likely pivot, and this generates an equilibrium, right? So actually what happens is that approval here is preventing this bad Duverginian equilibrium. However, this is not the end of the story. Why? Because approval voting admits bad equilibrium. So look at this bad equilibrium. So actually this situation is as the previous one with the green voters and the blue voters, in which I have just added a small number of orange voters, okay? So these orange voters, right? So I still have 60% of green voters as before, ABC, 30% of blue voters that prefer C to B to A. And what I did is I added a small sample of voters, 10%, that prefer B to A to C, right? So they prefer this middle candidate. Again here, A should win, right? A is the first choice of 60% of the voters, right? But what happens, so is the Condorcet winner, it's more than the Condorcet winner, but what happens is that with approval voting, B can win. So how can it be the case? So take again the situation in which everyone thinks that either B or C is going to win the election. Now, the blue voters should only vote for C because they prefer C. C is their top, and either C or B is going to win the election. The orange voters should only vote for B because they like B, and only B and C are going to win the election. And what happens with the green voters? The green voters, they prefer A, but they don't mind B. I mean, so B is the middle rank candidate. So they're going to do is they're going to vote for A and for B. So these generate scores 60, 70, and 30%, right? And this is what I'm going to skip here. Some computations actually show that now in this situation, the most likely pivot event is B against C. So this, and then BA, and then AC, and this again is generating this, right? This generating these best responses. So here what we have is an example in which we have a Condorcet winner, and this Condorcet winner is not elected by approval. But so this is a typical situation in voting rules. Okay, in general, you feel that approval voting is better than plurality, or could be that you prefer border to some other rule. But in general, you can always find a profile, a preference profile, in which it admits bad equilibrium. Okay, so situations as this, in which obviously A should be the only winner, but actually B also wins. So what we're going to do in the paper, okay, is to show that, okay, this equilibrium that failed to select the Condorcet winner is not very frequent, okay? So what we're going to do is to build an algorithm, right, that computes all ordinal equilibrium for each possible preference profile and show that the previous situation I just showed you is a bit particular. So in the end, we should not care that much about this situation. And then on the second part, I will talk about this learning procedure. So I still have 15 minutes. Okay, good. So now, I mean, there is a literature. I mean, I don't want to review it. I don't have time to do this. I mean, it's related to a lot of papers. It's also related to IC and IIC literature. But well, let me go into the model, okay, given the limited amount of time. So the model we have in mind is a Poisson game, okay? Why a Poisson game? Well, let's say that it simplifies the computations to be done, okay? Because it unifies the beliefs of the voters. So what we have is we have three candidates, A, B, C, right? And voters, and the number of voters is random, right? It's drawn from a Poisson distribution of parameter n, which is the expected size of the population, and this is common knowledge. So the type of each voter is going to be ordinal type, so it's going to be denoted T, and it's divided in two settings: O, the ordinal type, so ABC, ACB, BAC, and U. What is U is the utility for the second preferred candidate, right? So utilities are normalized. So I'm only talking here about approval voting. A similar idea can be done with plurality and the other rules. So the strategies are as follows. If you are an approval voting voter here, you're going to make a strategy which is from your type into the set of messages. And the set of messages, what I said before, is the set of approval voting ballots, right? A, B, C, or double vote for AB, double vote for AC, and BC. This is going to generate a poll for ballot, right? So what is tau of M is the share, right? Remember, rho is the probability distribution. So it's the share of types in the election that are announcing to cast ballot M. So this generates that the number of ballots in the election is again a Poisson distribution with size n to m, and the score of the candidate K is still random, and it's the sum of this Zm in which K belongs to the ballot, right? In which K is approved. So this, now from the individual point of view, this gives us an expected utility given a poll, right? So voters, the way they reason is there is a poll tau. They have their beliefs, or they have the beliefs on the poll, they have their types, and what they do is they compute the expected utility, right? So they have a probability of each of the outcomes, right, times the average utility of adding ballot M in the event that the realized outcome given the poll T tau arises. So this defines best replies, expected score, expected winner, and well, this gives us the equilibrium notion we want, right? So, I mean, this is the technical part of the model. I mean, I wanted to show you the data. Let's say that the only thing I want you to remain from this slide is that, if you are a type ABC, independently of you, right, your best response is either to single vote, like to vote only for your best element, if your utility for your middle rank candidate is low, and you're going to double vote if your utility for your middle rank candidate is high. So what is this U0 infinity tau? Is actually the utility threshold, which is going to be endogenous, right? It depends on the strategies of the rest of the players, and it depends on the profile. It depends on the preferences and on how they behave. So given this, we define an equilibrium, right, as a self-fulfilling pole, right? So a pole T is an equilibrium if the best responses at infinity, when n goes to infinity, coincides with the initial pole. And an ordinal equilibrium is an equilibrium in which the utilities don't play a role, right? The intensity towards your middle rank candidate doesn't play a role. So Vincent, how much time do I have? Vincent?
Already consume your time more or less, so I would let you 5 minutes.
5 minutes, okay. So just let me show you two things, okay? So the first idea is the algorithm allows us to compute the probabilities of this bad equilibrium to arise, right? So this bad ordinal equilibrium is the equilibrium I show you in this example with these orange voters. So as you can see here, right, So K is the number of ordinal profiles, right? So the probability of having a Condorcet winner with 3 alternatives is pretty high, independently of the number of ordinal profiles we have. And the probability of having this bad ordinal equilibria is pretty low, okay? It's, well, with six utility ordinal profiles is less than, it's around 0.1%. Now, the only thing I want to, the last thing I want to show you, right, is the learning procedure, okay? So what we have is, we have a learning procedure in which actually voters update the way they vote at each step, okay? They start with a uniform draw. At each step, some share of the voters update their vote by best responding to what they should have done before, to the previous step, and some don't update. And then what we have, okay, is these probabilities, okay? So what we have is starting with a uniform draw, probability of convergence of this learning procedure is going to be very high for both plurality and approval voting, right? With, and you know, the most interesting data here is that when there is a Condorcet winner, approval voting selects the Condorcet winner 100% of the times, and in the single peak domain, 99% of the times. Whereas with plurality voting, we only get this selection of the Condorcet winner, roughly speaking, on 2/3 of the time, right? So here, this slide shows that actually the efficiency of approval voting in this learning model, which is based on Poisson, is pretty high. So, I mean, we can do some things on precise profiles, okay? I mean, I can show you some precise profiles, namely, I mean, on the divided majority setting, but this is maybe not the main thing I want to show you. So this just 2 slides and then I go to the conclusion. So namely, how do people vote, right? Because we can now simulate all these equilibria for all preference profiles. So what we have is that, you know, how do people take advantage of the strategic possibility with approval voting of single voting and double voting? So this is given all preference profiles. We have that 50% of the voters vote for their favorite candidate only, 20% only for the 2 first, right? And 30% are going to decide on the basis of the utility level. Finally, on simulations, what we can prove is that the winner in any equilibrium that we obtain gets always 50%, gets more than 50% then of the scores, right? So, and the rest of the candidates gets less than 50% of the votes. So this again pushes towards the idea that, you know, the winner cannot have legitimacy concerns with this. So now let me go to the conclusion, since I have went over my time. So what we do in this paper is we're going to study strategic voting by adding a numerical analysis to strategic voting, right? So the previous papers were focusing on particular profiles and they were analyzing the set of equilibria, right? Here, what we do is we go 1 step further and we kind of compute the likelihood of the bad equilibria of the different rules to vary. So what are our conclusions? Well, the first conclusion regarding plurality, I think, is pretty well known. Plurality enables coordination, but the outcome is pretty indeterminate. Approval, on the contrary, is going to permit coordination when a Condorcet winner exists and almost never admits bad equilibria. And with this learning procedure, we're going to be, we can prove that the Condorcet winner is almost always elected when we have this idea of fictitious plane. Well, we have other feeders. We also have a comparison with negative voting that we also show that approval dominates. But well, let's say that's all I wanted to say. So thank you very much.
So we have a question by Klaus, and I have almost the same question.
Okay.
So the famous question, what about more than 3?
1 second. So what about more than 3?
Both the theoretical part and the simulation part, maybe.
Let's say that technically speaking, with three alternatives, approval voting, it's more, I mean, if you remember the slides, I mean, I can maybe go back to this slide that maybe is going to show you the difficulty. So this slide, right, shows how people vote in these games with approval voting, right? Namely, if U is low enough, they single vote. So the intensity for the middle rank candidate is low enough, they single vote. So they only vote for the top. And if U is high enough, they double vote. When you go for more candidates, I think we will need special assumptions, right, on how they vote, right? Because there are papers that show that need not be the best response need not be sincere. I think technically we don't yet know how to do it with more alternatives. And most of this literature, well, except the contribution of Jean-François on this leader rule, is on three alternatives. But I agree with you that it's a very important question. But given the difficulties on having the algorithm and computing this threshold that converge, I think three alternatives for the time being is enough. But I agree.
So, if I can continue, the algorithms you have to compute the equilibrium is very sensitive on the fact that you have three candidates. You cannot generalize it in some ways.
I mean, the expert on the algorithm is François.
Yes, that's why I'm asking him.
But I mean,
yes, maybe I can answer, Matías.
Sure.
Just to answer your question, Vincent, the fact is the algorithm is not maybe in the sense that we can think of it usually. Usually, for example, you do Monte Carlo drawings or stuff like that.
Yes.
Here, the algorithm relies on a mathematical proof of the best response to a given tau vector.
Okay.
And so we just apply the mathematical results that we have to compute the best results. And then the computer part is just to do the iteration of the learning process and so on. But fundamentally, the result is a math result. And this math result, we have it for three candidates, and it's very, very difficult for four candidates.
Okay. Another question by Janik Peters.
I'm not quite sure if it is a relevant question, but why do you use a Poisson distribution to sample the size of the electorate?
Yeah, so actually, I mean, there were, since I think the 70s or the 80s, there were a lot of models that try to estimate pivot probabilities, right? And often they rely on combinatorial techniques, right? So Meyerson at the beginning of the 90s, well, end of the 90s, proposed this Poisson idea. Why? Because let's say that it minimizes the computational problems, right? Because there is one key idea, which is that the beliefs of each voter in the election is identical, right? So typically, if you have a fixed size of the electorate, you have n voters, and there is randomness on how voters on the number of votes of each side. The belief of each voter is going to depend on the identity of the voter. Meyerson shows that actually these beliefs are independent of the voters. So the belief each voter has on the electorate is the same as an external observer would have on the model. So this is why the literature has focused on Poisson. I mean, not all, right? There are other models, but Poisson simplifies a lot of technical difficulties here.
Here also maybe to complete Matías' answer. So there is this property of environmental equivalence that Matías just mentioned. And there's another property called independence of actions. And in fact, when you put these two properties together, the only model that satisfies them is the Poisson games.
So independence of actions, meaning the number of people who choose a given ballot is a random variable, which is independent of the one that describes the number of people who choose another ballot. So this independence is going to be, of course, a lot of, if you have to deal with correlation in these models, then things are going to become very, very hard.
So, do you have any other question? Nope. So we will thank again the speakers. And maybe, Edith, I can let you announce the next seminar if you're still with us.
Yes, sure. So our next seminar is planned, I believe, for December 3rd. So 3 weeks from now, rather than to avoid the American Thanksgiving, right? And we are going for an alliteration. We're going to have a Berlin seminar by Robert Vedrak and Marcus Brill.
Thank you.
So thank you all. Thank you. See you in 3 weeks.
Bye-bye.
Have a good Thanksgiving for those who will have Thanksgiving.